Hi everyone, I'm pleased to be here today to talk about a technical project, a research project that we conducted for Ohio Department of Transportation. This is about pier caps and how we can load rate pier caps to more accurately identify the overloaded situations. We conducted this study together with two master students, Papu Bania as well as Anish Sharma. Let's get started. I'm going to start with an introduction, objectives, methodology. Strut-and-tie modeling is what we did. That's the main part of the study. Verification is very important to us. We verified the methodology using nonlinear finite elements as well. And I'm going to finish with a set of conclusions. Pier caps, we all know, we all are familiar with pier caps. They are transitional elements. They move point loads from girders to columns. It's an intermediate element. It's really important for the long-term performance of the bridge in the long term. So in Ohio, we have 28,000 bridges approximately. And if you account for a minimum of 3 pier caps per bridge, 100,000 pier caps. It's just a large number. It's a statewide number. If you look at nationally, 600,000 bridges, and if you multiply this by 3, you are going to get almost 2 million minimum number of pier caps. So it's a lot of pier caps we have. We need to load rate bridge elements as a regular process. When a change occurs, the change might be increased loading, it might be increased traffic, some concerns, and so on. So we need to analyze them to determine their capacities. And it happens to be the case that these pier caps, whenever we analyze, more than likely we find them to be overloaded. However, if you inspect them on site, they look pretty nice. No cracking, no excessive deformations. They look just as normal as you would expect. So the question is, what is the issue? Is it the analysis method? Why are we finding a lot of pier caps to be overloaded? So that's the research question we looked in this study. The issue comes down to limited funding, right? So you want to identify the real overloads and use your public funds wisely, only to rehabilitate those overloaded bridges. And to do that, load rating is very important. So you want to calculate load rating accurately. So that's the main focus of this study as well as my presentation today. Just as a reminder, load rating is the live load carrying capacity of a bridge. This is a very rough conceptual equation. It's an ultimate limit states design. You need to factor everything, but essentially the capacity includes dead load and live load capacities. You deduct dead load effects and you divide it by live load effects. So that would give you how much you can exceed the current live load capacity. Can you get 20% more live load on it, 30% more, or is it overloaded? So that's this process RF will tell you that. Capacity is the most critical aspect because dead load, live load, we have certain confidence in those. My presentation is entirely focused on the capacity determination. So our objective is to determine or develop an accurate analysis method, again, for capacity calculation, only for pier caps. And we did that by developing computer program STM-CAP, which I'm going to come to that in a minute. It's a strut-and-tie method. Developed solution, it's important to verify the developed procedure. So that's what we have done, as well as we compare results with the finite element as well as sectional analysis methods. So that's pretty much what you are going to see in this presentation. This plot is coming from 1964. The data comes from 1964, but the plot is more recent. You can see here the experimental results from Kani tests conducted at the University of Toronto, Canada. And if you plot these on normalized shear strength versus shear span to depth ratio plot, you will see that it goes exponentially, right? So the smaller the shear span to depth ratio, the stronger the beam is in shear, right? So that pretty much explains or answers my research question with regards to what is going on for pier caps, because pier caps are typically deep elements. They have shear span to depth ratios commonly less than 3 or more than likely less than 2 in many practical cases, which qualifies them as a deep member. So if you use the traditional sectional method, which we keep using it, I'm going to remind you what it is in a minute, you're going to get the capacity calculation or prediction following the red line here, right? And that would be super conservative for deep members such as pier caps. So that's really the reason why if you use this method, which is the commonly used method, you would find things overloaded because you would predict capacity to be significantly less than what it really is. So shear span to depth is, shear span is the distance between support and the point load. Depth is effective depth, so this plot shows that. The best type of calculation that you can do is to use sectional method up to this transitional point, which is shear span to depth ratio 2.5, and anything less than that or anything deep, you need to use strut-and-tie method. So this is in H2 as well as other codes, which I'm going to show you in the next couple of slides. So a typical pier cap, let's say shear span to depth ratio 1. If you analyze it using sectional method, that's going to be the capacity you would find, which is, let's say, 0.05. And if you analyze it using strut-and-tie method, you're going to get 3 times larger capacity, which is more representative of the real case. So that is, that's the potential that we investigated. We looked at how to benefit from this deep beam behavior using strut-and-tie method and more accurately determine capacities and more accurately identify overloaded bridges. So again, it's that's the ratio is the most important aspect. To be conservative code, H2 goes with 2, which is fine. If it's less than 2, you have a deep member. If it's larger than 2, you have a slender member. No worries with slender member because most members that we deal with qualify for a slender member. We know how to analyze them, which is sectional method. Deep members definitely more challenging to deal with, and it's not common in engineering practice. We don't know, or engineers do not know how to analyze those. H2 as well as other international codes, including Eurocode or Canadian highway design guidelines, recommend using either strut-and-tie method or nonlinear analysis method. So when dealing with deep beams such as pier caps, you pretty much have 2 choices. This is not a choice. Sectional method do not apply. If you use it, your predictions would be extremely conservative and you would find everything to be overloaded. If it's a deep member, which is typically a pier cap, it's going to be overloaded. So that's the issue. I'm going to show you how to determine whether it's a deep member or not. Depth is not the only parameter of being deep or not, so the look will not tell you that. So what you need to do is to create a square which is dimensioned by, call it D by D, effective depth by effective depth, and put these adjacent to your support reactions as well as point loads. See, for example, this region is entirely deep region, right? So they overlap very significantly. So here shear span depth ratio is a bit over 1, which is a very deep region. So keep doing that, and as you can see for this pier cap, it's entirely, your squares would be overlapping, and you're going to get an entirely deep member, which is a very common situation for pier caps. Sectional method, this is a quick reminder. We use this very often. It is applicable to slender members, and it's based on drawing the shear diagram, moment diagram, determining the maximum forces, as well as checking your section at critical locations. You know, the code tells you that for shear, go this distance away from the support. For moment, check it, you know, at midspan, check it under the point load. So the check is done by section. So you determine critical sections and you only check for those sections. That is why this is called sectional method. Sectional method uses a very important assumption, which is plane sections remain plane, right? That assumption is the basis of engineering beam theory, which is true for slender members, right? That's the reason why sectional method do not apply to deep members, is that deep members do not satisfy that requirement. So deep members do not exhibit a behavior in which plane sections remain plane. It doesn't for deep members, so that is making engineering beam theory invalid, so that you need to use, you know, either a strut-and-tie method or a nonlinear finite element method for deep members. Strut-and-tie is the first candidate for analyzing deep members. It is based on a logical stress flow, right? So the stress will move from load application point to the support using the shortest, the most direct, the easiest path, right? So based on this, you create your thrust model and you analyze it. So, you know, in essence, strut-and-tie method easier than the sectional method because it only uses tension or compression. There is nothing else. There is no shear force, there is no bending moment, there is no torsion. It is only tension or compression, right? It uses stress flow concept. So it is a really basic, really simple method, and I'm sure you visited historical structures coming from centuries ago, and you would visualize that at that time, you know, there were no computers, there were even no calculators, and strut-and-tie would be one way that those early engineers conceptualized the stress flow and sized the members, or determined where to put the columns, where to put the beams. So strut-and-tie is such a method that you can use it without any calculator, any computer. You can even do it at the back of an envelope. So it is not a calculation intensive process for creating the preliminary design as well as checking an existing design. So there are 4 elements in a strut-and-tie method. Struts, which are compression elements only. You have ties, which would be your reinforcing bars, and you have nodal zones, which are arguably the most complicated aspect because of different geometries depending on how your struts intersect. So these are 3 elements plus the 4th element, bar development. So in order for you to be able to develop the deep beam action, that reinforcement must be developed, right? So the reinforcement development is not something super critical in sectional method, especially at the supports. In a simply supported beam situation, you don't really care much about rebar development at the supports. In fact, we just cut it at the support because the moment is zero, right? At the support, rebar is not needed. That's not true for deep beam action. So stress is uniform. And you got the stress in this situation same at the support as the midspan. It's the arch action, so it's really important for a valid strut-and-tie model to have that rebar development, right? If it's not developed, you reduce the capacity, right? You reduce the capacity. So there are ways of dealing with it, but in a new design, you want your rebar to be developed. So this is just a summary, tension compression as well. This is another conceptual. This is a real bridge in Ohio. As you can see, pretty short spans. What is going on? Let's take a look. So I'm seeing, for example, this is pretty short span and the compression directly goes into support. But if the span is a little bit large, you need to use a tie to lift up that stress. For example, this span is larger, maybe around 2-ish, still a deep member. So what you can do is to shoot it at such a point, lift it with a tie, which is going to be your straps, and then shoot it again with compression, and that reaches the support. So there's a logic with this. I'm not targeting to teach how to develop strut-and-tie methods, because you need to take a course and spend several months on it. But this is a conceptual visualization of developing a strut-and-tie model for that. So here you can see, struts. You will see ties, which whenever you have a tie, you need to have a reinforcement. You cannot put a tie if there's no reinforcement, because tie equals to the reinforcement, right? And nodal zones, as you can see, you got everything. You got square, you got rectangular, you got parallelogram. These are a little bit making it a little bit more challenging when you check the nodal zones. So the issue is that it's a little bit too conceptual, right? Engineers are not familiar with the method. There is no equation. It's not equation based. It's a conceptual. It's really easy to calculate or not calculate. It's very easy to develop invalid models, more than likely. So that's one danger with this. It's an iterative process. Your first model will never be the best model. So you would start with something easy, refine it. So you would need at least 2-3 models throughout the process. So we explored the potential of applying this in an automated manner, removing this iterative, labor-intensive, subjective nature using some methodology only for one member. You cannot do this for everything, right? So this is only for Pier caps. We focused on Pier caps, and that was the objective of this project. And we developed the tool, which is STM-CAP, which develops models, checks it, refines it, improves, optimizes it, and so on. So it is a specialized tool for Pier caps only. It has quite a few modules, 5,000 lines of codes. We didn't want to create a new program because new program requires a learning curve. What we did was to incorporate this using Visual Basic Application Language into an Excel spreadsheet. So you can easily, everybody is familiar with Excel, and you can use this without a need to install or learn a new program. So that's what ODOT wanted, what we wanted to reach a broader audience. It's free. This is a research-based contribution. It is not commercial. You can use it. It's posted in our University of Toledo website. You can download and you can use it. So again, you need to develop a valid model, which STM-CAP is intended to do. It uses HTO LRFD 2017 to 2020 version. There is nothing changed with regards to strut-and-tie model, so it's still valid. And the program gives you graphics. We spent a lot of time doing this to scale graphics in Excel because you want to really visually see, and you see the utilization ratio. If you see 0.71, meaning that 71% utilized, you have 29% more up to the capacity. If it's 1, it's in capacity. If it's larger than 1, it's overloaded, right? You see reactions. These are all US units. These are KIPs. These are just ratios. There is no unit associated with it. And ties, it's a typical international color scheme. It's red. Struts, we use blue. Sometimes, in some other references, you see them as black. Nodal zones is just the intersection of ties and struts. These are utilization ratios, and the program will give you the table, and you will see what passes, what fails. There are color coding and so on. I'm just going to show you how it works. So this is how the program opens. It might take a while depending on your computer speed. I'm using a very inexpensive laptop, so it might take 10-15 seconds for initialization. So you see the welcome screen. The input cells are shown with orange, right? So output cells are not editable. So the color scheme will identify that. As you can see, that those orange cells, you can input the numbers, how many columns do you have, and when you press generate, the graphics will be generated based on the scale dimensions, and you will see that. You can use asymmetric function if it's not symmetrical. Most of the case, we idealize Pier caps as symmetrical. This is showing half of it for a symmetrical situation. You see all distances, what's C1, what's C2. You need to input all of these in orange cells. Is your pier circular, rectangular? You need to input that. There are loads. You may not have all of these. You can generate the load table just to get you started, and then modify it as needed. If the load is not present, you can input 0. Once you're done, you need to regenerate. This is going to be the final model, including your actual load conditions. This is what we are doing. This is a real bridge located in Ohio. You see the situation here. This is a check whether it qualifies as a deep member. If it's not really deep, you don't have to use this. So we check this at the very beginning before you spend time to input everything. More than often, almost always, VC qualifies for deep. But if it's not deep, you don't have to proceed. You can go back to your sectional method and you don't need to use this. This qualifies for a deep member, so we are proceeding with material properties. Resistance factors, these are from HTO. You don't have to change it, but if needed, let's say the number changed in a future revision, you can change it from here. The program gives you regions. Region 1 is cantilever, region 2 is above the first pier, and so on, and your input would be region by region. We added also static graphics to show you what you are inputting. What's the top rebar, what's the bottom rebar, what's the clear cover, and so on. And you have to input this for each region. More than often, rebars would be constant, so it's not going to change frequently. So it's more than likely, as you see from this example, all regions have the same rebar, same centroid, because it's typically continuous from side to side. Stirrups, again, how many layers do you have? What's the spacing you're inputting it into this box? Crack control reinforcement is important. Whether you have it or not changes the calculation. So you input that. Hopefully your Pier cap has that. Base plate dimensions. There are some static images shows you what is with what step. Reinforcement development is again super important. If you have a hook, which is good, that reduces the development length. If you have a hook, you input that information. Again, you're not inputting a lot. You're only inputting the orange input cells. Some drop-down menus you can pick, is it epoxy coated or not. So the coefficients would change depending on the situation you input. This is the model, output model. It might take 5-10 seconds to generate depending on your computer speed. So we got it, analysis done. This is the result. So, if you are familiar with the process, you can get one bridge analyzed under 5 minutes. If you have used this before, you see everything passes. I'm seeing here the stress ratios are not even close to 1. It's below 1. This 41% is less than half of the capacity of the member. I'm seeing 0.5%, not percent. I'm seeing 0.5 utilization ratio, which is 50% of the capacity. So you can see everything passes. We also gave you some optimization possibilities, whether using ties or not. So as you can see, by default, program choose to use one tie only in one of the regions, which is shown with 1. If you see, you can try, remove that tie. Is it going to help? Removing the tie, it would reduce your angle, and it's going to load your struts more, right? So if you have a strut critical situation, it's not going to help. But in this situation, struts are, not heavily loaded. So again, see, it passes. So you might get away, if this is a new design, you might get away by not using stirrups for that region because you have the capacity for that. You can see the consequences. You can compare different options. There is also bearing check, which is done automatically. Bearing 1 is at the top, bearing 2 at the column or pier location. There's a lot of calculation going on at the background. It's hidden. You don't have to check. You don't have to recheck it. And I'm going to show the verification studies. But this is for recording purposes. If you are creating your project folders, you may want to create a PDF file, and these are the details. These are how the capacities are calculated, how the strengths are calculated, and so on. So you can see all details. If you are doing hand calculation, you can check those numbers with what we calculated here. This is matrix stiffness method. It does a truss analysis. See, these are truss forces, reactions, and so on. So there's a lot going on at the background, but you don't have to get involved with these unless you want to. So that's pretty much it with this. You can see for this one you can create 4 different models using vertical ties or not. For example, this one, if you are not using vertical ties, you have an overload situation. So this member is 32% overloaded, so you should use the vertical tie. If the member do not have vertical ties, then that pier cap would be overloaded. So you need to rehabilitate it for shear, because that indicates a shear failure. The other situations, as you can see, if you use a vertical tie, your strut angle will get steeper, which is always a good thing to do. It's going to reduce your stresses. But I mean, this is also good as long as it's not overloaded, which is fine. And if you are designing this from scratch, you can get away by not using vertical ties, which is permitted. It's still, you have 25%, 24% reserve in Model 2. So this is the same pier cap, but different conceptual stress flows you can see. You can see the overload location. This is, if you see an overload at the horizontal reinforcement, it's a flexural overload. This is a shear overload. It's a diagonal member. You need that shear reinforcement, maybe perhaps FRP wrapping. Compression overload would be at the horizontal or vertical compression elements, which are struts, right? So it's overall a pretty fast modeling process, and we try to educate the user. That's what we do. We are educators. You would learn what's going on with strut-and-tie method, and you consider the deep beam action, and you consider you get the largest capacity as compared to the sectional method. We verify this using a general purpose strut-and-tie method. I don't want to get into too much details, but just want to show you comparisons. It should be very similar, and we got very similar results using another tool. We modeled 8 pier caps. We got the drawings and information from Ohio DOT. So these are real pier caps located in Ohio, Columbus area. Nonlinear finite element is the second option, which I showed you at the beginning based on HTOP. It is good. It's going to be very accurate, but there are challenges as well with this one. It's a little bit more complex than strut-and-tie as well as sectional method, but we want to see how it compares with strut-and-tie. We used a program which is called Vector 2, developed at the University of Toronto. It's a high fidelity advanced nonlinear finite element modeling platform specifically developed for reinforced concrete, modified compression field theory, which is an internationally recognized theory, which is also used in HTOP. If you check the shear calculations, it's based on that. It's a semi-rotating crack model essentially, and there's a lot of details on this. I'm not going to go into details. We modeled those 8 pier caps using nonlinear finite element. We determined, because this is going to give you everything, right? So you're going to see the stress contours, stress flow, critical locations, and so on. But you need to, for comparing apples with apples, you need to convert them to utilization ratios for comparison with STM-CAP. So that's what we did. We calculated the average stresses at each region, divided it by the capacity, and got the utilization ratios, right? These are the numbers which we got at the critical locations. And we compare these with strut-and-tie STM method. And I think in the next plot, we got good correlations with that, but nonlinear finite element would be expected to be more realistic. And as you can see, nonlinear finite element gives you even larger capacities because it benefits from lots of additional mechanisms. Maybe I'll mention only one major one, which is concrete in tension. In a strut-and-tie, you assume that once a member cracks, concrete disappears. It's gone, which is not realistic, right? You have still concrete, and there's mechanisms called tension softening, tension stiffening. Once a concrete member cracks, it would still transmit tension because you have aggregate interlock, you have reinforcement crossing cracks, this and that. So a nonlinear finite element would capture these effects, and that would improve the capacity On the other hand, strut-and-tie, you don't have these. Once a member cracks, you are relying 100% on the reinforcing bars to transmit that tension. So the concrete is gone. You don't have any concrete after cracking. So as you can see, finite element is pretty constant across different span depth ratios. It converges to strut-and-tie for very deep members as well as slender members. I'm not saying very slender because slender starts after 2.5. So a typical slender member has shear span depth ratio 5, 6, 7, 8, right? So which is not shown here. So for those regions, you should get good or similar results. For those regions, you don't even need to use STM or nonlinear finite element. You should really use the sectional method, which is a couple of equations, super easy, and we use it on a daily basis. I'm sure you are very familiar with the sectional method, so you don't need these for anything over 3. The issue with nonlinear finite element, it is time consuming and it requires significant experience. It's not suitable. You cannot just open the program and start modeling things. It's there's a significant learning curve. You need to study it, maybe a master's degree, maybe a bit more. So it is definitely experience intensive process. Sectional method shouldn't be used, but just for the sake of demonstration, we used it. And in almost all cases, the capacities are 2 times larger, or the utilization ratios C is 2.45. So it's going to be overly conservative for deep members. This is my favorite plot. This is because this explains everything. It's a very neat plot. Vertical axis, the utilization ratio. Smaller the number, the better, because it's less utilized. Larger the number indicates overload. So if you look at your sectional method, which is the red prediction curve, it diverges quite a bit for deep members. So it's really predicting loss of stresses, loss of utilization ratio as compared to other two, which is STM-CAP, nonlinear finite element, right? So, the conclusion with this is that shear span depth ratio is smaller than 3. Expect significantly conservative predictions if you end up using sectional method, which really you shouldn't, because it's not intended for deep members. Comparing these two, you can see that strut-and-tie method is a good compromise. It diverges from sectional, and if the member gets deeper and deeper, it's really converging to the nonlinear finite element in terms of the prediction. It's in between, it's closer to the nonlinear finite element. So STM-CAP is also included in ODOT's bridge design manual. This is the July 2020, very recent version. So there's the download link. Also the full project report. So you can see all the details from the report. We published a journal paper. If you would like to read, you can download this from my website. It's freely available. You can just, I'm going to share this presentation and you can click on the link and you can get the paper. Project report, also it's just one click away. You can download, take a look. We have the full master's thesis, which is a couple of 100 pages. If you really want to dive deeper into these topics, you can take a look at the thesis as well. It's a contribution to the engineering community. It's not intended for any commercial profit. It's freely available, full version. You can just download it and you can test it out. Let me know how it goes if you have any issues or questions. We created videos. If you visit our YouTube channel, you will see very short videos. There are some 5-6 minute getting started videos. There are some more 15-20 minute videos with this, so you can look at those for training purposes, but don't hesitate to reach me out if you have any issues or any comments with regards to STM-CAP. So Conclusions, strut-and-tie is a very good method. It is fast, easy to use, and we implemented this using a Visual Basic Application language to provide a graphical solution, because we are engineers and we have to see. We have to see the numbers, we have to see the model, we have to see the results. It's quick, easy optimizations. It's not a closed box. You can see the calculations. You can also tweak a little bit using vertical ties or not for optimization. You can learn from it. It teaches how to develop valid models. The models should all be valid. There's going to be no other option, because it's a very focused tool only for Pier caps, and we considered all permutations when developing it. Pretty fast, you can get it up and running, and if you keep using it, you might even finish a bridge under 5 minutes if you are a fast user. You can make your capacity calculation and plug that into that load rating equation, and make more accurate decisions with regards to which one is overloaded, which one is not, and how to rehabilitate those. We validated this. You can get results from our reports. You can get up to 3 times larger capacities using the deep beam method. Accuracy in between. Nonlinear finite element is expected to be more accurate. Sectional method is not even applicable. But in terms of the time consumption, STM-CAP is not significantly different than the sectional method. So, we are finding it to be a very good compromise in terms of accuracy and effort. Effort is very similar to the sectional method, but the accuracy is also similar to a nonlinear finite element, which is much more time-consuming method. So that's pretty much it. I would like to finish with acknowledgements. We worked with ODOT during this project, and ODOT created a technical team, technical panel to talk to us every month, to provide us drawings, information. I know we consumed their time a lot. 2 master students as well as myself, we contacted them a lot, but I would like to really thank them very much, as well as Ohio DOT in general. If there's a single reason why this project existed, why this STM-CAP is existing, that's ODOT. So without ODOT's funding, there wouldn't be any STM-CAP or any program for this purpose. So I thank you very much for your attention. I'm happy to finish this on time, and I would be happy to discuss any questions, issues, and I would also be happy to hear any comments. Thank you.